Okay, welcome to one more video on the memories. So let us continue with the analysis of floating gate MOSFET. The floating gate MOSFET is also said as FAMOS, where F stands for floating gate, A stands for avalanche, and MOS is metal oxide semiconductor. Why this term A avalanche is coming is because, as we discussed in the previous case, okay, let us start the analysis again. If you consider a normal FAMOS transistor under normal condition, we have this as the transistor configuration with the what cross section we looking like source, drain, and receiver bulb. There's a gate, and we have one more gate which is there floating between the this gate and the oxide, that is the interface here. Now typically when there is no charge that is trapped in this floating gate, the typical cut-in or the threshold voltage happens to be 0.5 volt. So if you increase, if you have the gate to source voltage anything beyond 0.5, the channel will get created and we're going to have the transistor will be turned on condition. That is under normal condition when there is no charges that are there trapped on this gate. It is possible to change the threshold voltage of this particular transistor to beyond 2.5 volts by injecting some negative charges, that is in the form of electrons, onto this floating gate. That can be accomplished by having a sufficient voltage across the gate and the source. Okay, let me assume that this is 0 volt and this is 20 volt. This will ensure that you have a lot of electrons being accumulated over here, so that you don't have an inversion of the channel. And then you apply 20 volt across this. Now you can see there's a 20 volt applied across gate and source, and there is another 20 volt applied across drain and source. Because of this heavy potential of the gate to source and heavy potential between drain and source, electrons starts flowing at very high velocity. And because of this voltage, there are possibilities that since the oxide layer here between the floating gate and the substrate is not very thick, it is in terms of few angstrom, so there is a possibility that the electrons which are flowing in this direction may tunnel through and then settle down here. Now as the number of electrons are settling down is keep on increasing, the threshold voltage, which was 0.5 volt, will be now increased to 2.5 volt or 3 volt. Because why this threshold voltage will go from 0.5 volt to 2.5 or 3 volt is because whenever we have no charges accumulated here, it was just sufficient to have only 0.5 volt. Whenever you have the electrons being accumulated here, we know that electrons are negatively charged. So if you want to have the channel to be get formed, we need to first overcome the charges that are there in this floating gate structure. Now why the charges are accumulated here is because you have applied 0 to 20 volt and then 20 volt is applied here, which made the electrons to settle down here. So once the electrons are settled down here, now of course this 20 volt and 20 volt here is required to change the threshold voltage of this MOSFET. If at all, if you don't want to change the threshold voltage, no need to apply 20 volt. So assume that you want to change the threshold voltage of this to more than 0.5. Then we have made this configuration. Assume that it has set to 3 volt. Now there are some charges here. Now you have applied the threshold voltage of this FAMOS has become 3 volts. Now you apply 0 volt here, 5 volt. This is a normal operation. This is an operation that is required to enhance the threshold voltage, and you apply some 2.5 volts. Because usually this gate, which will be connected to word line of your memory, of course when I say word line is equal to 1, even 2.5 volt will be considered as high, because any voltage greater than the normal threshold voltage of 0.5 volt can be considered as word line is equal to 1. So any voltage less than 0.5 will be considered as word line voltage equal to 0. So let us assume that we want to have these as the values to be stored in these particular MOSFETs. So these are the MOSFETs, or this is a particular bit which has to store the value of 1, and this should be 0, this should be 1, this should be 0. Now assume that in the previous case, suppose you want to implement, so if I just come here, how we were getting this value of this, suppose if I consider this particular bit, so how we were getting it as 0 1 0 0, we were getting it as 0 1 0 0, because at this bit line I should get a value of VDD is equal to 1. So this transistor should turn on whenever the word line is high. Whenever the word line is high, I have to have my bit line as equal to VDD. So that is possible if this transistor is turned on. So what we have in this case is we have transistors in all the places, that is not only in the selected places. So as you can see here, since I was supposed to implement 0 1 0 0 and 0 0 0 1, we had transistor, of course in this particular case it is not 0 1 0 0, it is actually 0 1 1 0. So 0 1 1 0, so this is the value that is being implemented. Okay, for this one it is 0 1 0 1, and for this it is 0 0 0 0, then it is 0 0 1 0. You can see wherever it is you want to have a bit of 1, you have a transistor of lesser threshold voltage, which is far less than 2.5. Since you want to have a value of 0 to be stored here, you're not putting a transistor. So let us come back to this. Assume that I want to have this value to be stored. You can see now this should have a value of 1, this should have value of 0, this should have a value of 1, this should be of value 0. Now whichever bit you want to have it as 1, the threshold voltage of this should be, let it be 0.5 itself. Let it be 0.5 plus, because whenever you apply a word line voltage WL of 0, if it is 2.5, does this conduct? This conducts. You will get a BL0 as 1, that is logic high. You will get it as high. Now what is the value that you are supposed to get in this BL1? So BL1 should be 0. Upon putting 2.5, this transistor should be turned off. So this transistor should be turned off means the threshold voltage of this should be more than 2.5 volt. Because why it should be more than 2.5 volt is because this transistor, if this also turns on, then on this bit line 1 also I'll be getting a VDD, which I don't want now, because I want to have a voltage of 0 here. So the threshold voltage of this has to be changed to more than 2.5. So let us see how do we change, or how do we make the threshold voltage. Wherever you want to store 0, you have to increase the threshold voltage of this. Okay, let me just identify. Okay, this threshold voltage has to be increased, and then this threshold voltage is increased as per this, and for this I need to increase, for this I need to increase, and then for this I need to increase. And how about this? Because wherever you want to store 0, you highlight that transistor whose threshold voltage has to be increased. Okay, this has to be increased, this has to be increased, and then these rounded one should have VTH greater than 2.5. Why 2.5 is because we are assuming that let the word line be 2.5 whenever you want to make that line as high. So let us see how do I make this particular first row of transistor with different voltage. So as we know here, you make the, because this is now you can see this is, what is this? This is gate. You first make this equal to 20 volt. I have made this equal to 20. We just want to make this threshold voltage of this more than 2.5, this also more than 2.5, for which the condition is this. I want to make the gate of that particular set of transistors 20. So you make this equal to 20 volt, which is made here, and you make the ground of that particular, of course this is the source, this is the source. You can see this is source, this is source, this is source. So whichever transistor you want to make it higher threshold voltage, you just ground it. So I have grounded this, and then I have grounded this. So when I ground these two, and I'll make this also 20 volt. So upon making only these two grounded and making this 20, making this 20, is it not similar to this condition? See here, this is your source, this is your source point, which is now grounded through a resistor. This is your drain point, which is connected to 20 volt. That's what is here. And then you have a gate which is connected to 20 volt. Since you have a configuration of the voltages of these two transistors only, because even you can see here the transistor, this transistor and this transistor are also connected with 20 volt, their drain also connected with 20 volt. Since the source is not grounded, the threshold voltage of these two will not be altered. The threshold voltage of these two will remain as 0.5, whereas after applying 20 volt here and 20 volt here and grounding these two, the transistors, suppose if I name it as transistor 1, transistor 2, 3, 4. So transistor 2 and 4 will have an enhanced threshold voltage which can be more than 2.5 volts. So after doing this setup of making this 20 volt, grounding only these two, why we are grounding only these two is because the corresponding columns of these two resistors are these two. So then this will going to certainly enhance the threshold voltage of transistor 2 and transistor 4. Similarly, so we have enhanced the threshold voltage of these two transistors. Coming to second row, again I'll make this 20 volt. Of course, we have set these two threshold voltages more, then we can open circuit this, make this 20 now, and then of course you may have to ground the corresponding transistors. So you may have to ground this, you may have to ground this, and you may have to ground this. So upon grounding these three, upon applying 20 volt and upon applying 20 volt here, these three transistors will have the enhanced threshold voltage. Okay, once we make the corresponding rows and columns and VDD as the required voltages, the transistor which are rounded up will have a larger threshold voltage. Assume that the VTH of those transistors which are rounded up are made equal to 3 volt, So meaning, so out of 16 transistors, transistor number 1, okay, let me just take, this is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Transistor number 1, transistor number 3, 7, 10, 13, 14, 15 will have VTH is equal to 0.5 volt, whereas rest of the transistor will have a threshold voltage of 3 volt. So once this has been set, now I need to repeatedly read the values of 10, 10, 10, 0, 0, 10, all those things. So in such case, what I'll do, I will ground all the resistors. Now all the resistors are grounded. So all the VDDs are made 5 volt. So this is also made 5 volt. You can see VDD is made 5 volt. This was made 20 volt to initially change the threshold voltage. So in the normal reading operation of your ROM value, the VDD is still 5 volt. Now you applied 5 volt as the drain point. Now you apply 2.5. When I apply 2.5, since this transistor didn't had an enhanced threshold voltage, this turns on, I'll get VDD, that is 5 volt. Since the threshold voltage of this is increased to 3 volt, this is still off, I'll get a 0. I'll get, because this is grounded here, this is grounded here. So I'm getting 1 here because this is turned on, this is off because the threshold voltage of this has been increased in the previous process. Now it is 3 volt, whereas WLO is kept at a voltage which is less than the threshold voltage of this, which is now 2.5. Threshold voltage of this is 3 volt, so it is off. The output BL1 is actually 0. Coming to this, threshold voltage is 0.5. Word line is 2.5. It is on. You will get VCC here, and then here it is still off. So you could able to get 1, 0, 1, 0. Let us also see how the threshold voltage shifting can be seen here. So under normal condition, you can see this is the threshold voltage. This is the word line voltage. If the word line voltage is actually 2.5, whenever you actually apply, whenever you don't enhance the threshold voltage, it will be considered as on condition. So it will be representing a logic 1 here. Now you can see the same 2.5 volt is applied while reading process. Since few transistors have an enhanced threshold voltage, now that 2.5 for the transistor which have an enhanced threshold voltage, now they will be in off condition, so that you'll be reading 0 there. So it, of course, this is off means okay, it cannot turn on. You're actually reading a 0 from that particular transistor. Now you can see, suppose if you want to read what is the value here, make this equal to 2.5, make this equal to 5 volt, and try to read from this. Since it is 2.5, the threshold voltage of these three transistors are 0.5. All the three will turn on, and we will going to get the bit line 0, 1, 2 as VDDs, and this has a larger enhanced threshold voltage, which will going to, of course, which will not turn on for 2.5 volt. Then we're going to get a 0 on that particular line. So this way, because now assume that now this value of exact value of the memory, that is 10 10 00 00 00 10, and then okay, these have been set. Assume that these values have been set depending on the requirement. Now I want to change the value, so I want to reuse the same memory for a different application. Now it is still possible to reuse this. So first, because we know that the rounded transistors have an enhanced threshold voltage. Why they have enhanced threshold voltage? Because they have negatively charged electrons trapped in this region. So that's why they are holding the charges, and because of this the threshold voltage has increased from 0.5 to almost 2.5 or 3 volts. So since it has increased to 3 volt, it is still in off condition even when you make word line equal to 2.5. So in such case we are actually storing these values of ones and zeros. So assume that I want to reuse this for some other application. Next, what I have to do is I have to take out all the charges that are there in this particular transistor wherever the threshold voltage is enhanced. So what will happen is the charges which are trapped in these gates can be just again moved down to the substrate by exposing this entire structure to UV light. So under ultraviolet rays with sufficient intensity, these electrons can be released and they can again go back to the transistor, again go back to the substrate. So by exposing the ROM to a sufficient period under UV light, we can still make all the transistor to have 0.5 as the threshold voltage. Wherever you want to make the changes, you just make those changes, make the similar type of enhancement of that particular transistor to store as 0, then you can reuse the same transistor, same memory array for some other application. This way, unless you expose that entire array structure into UV light, the value that is stored in the form of zeros and ones, that is the lesser VTH or larger VTH, will going to remain permanently forever. So that's why it is called as non-volatile memory, but you can still make it reuse by exposing this entire device into the UV rays, so that UV rays will just bring down all these electrons back to the substrate. So it will be still of 0.5. Then you repeat the process to make wherever the threshold voltage more or less. So this way we can able to understand the working of floating avalanche effect in MOS transistor in the memories. So only limitation in this case in this type of memories is that we cannot expose these transistors very often to your UV light, because UV light will not only take out the electrons, it will also damage the very thin layer of your oxide and of course the thin layer of the metal conductors whatever you have. So it has got a limited number of exposure to UV light. Assume that it may have only 50 to 100 exposures. So maybe after 50 exposures, if you try to reuse that one, then the memory may malfunction. So that is one of the major limitation of these type of non-volatile memories, but which can be still erased using the ultraviolet rays. So in the next video we'll see how do we electrically erase the memory structure, so that you can able to use it very often, because that may not just reduce the lifetime of the memories.